Even and odd integers. The test absolutely loves to ask about even and odd integers. Do we know that k is even? Do we know that k is odd? This is a large category of questions. So this video and the following video talk about these questions. Let's start at the beginning here. These are the odd numbers. They go on forever in the positive and negative direction. These are the even numbers. They go on forever in the positive and negative direction. So notice a few things. First of all, 0 is an even number. This is very tricky. 0 is not positive, it's not negative, but it is an even integer. That's very important, and the test likes to ask about that. Evens and odds include both positive and negative numbers. So if you're told that x is even or y is odd, you cannot assume that they are automatically positive. They could be negative. But evens and odds pertain only to integers. Any non-integer is neither even nor odd. So if you're told x is even or y is odd, you absolutely know, it's guaranteed, those numbers are integers. Very important. All even numbers are divisible by 2. Even numbers can be expressed as 2k, where k is any integer. The prime factorization of a positive even integer greater than 2 absolutely has to include 2. Now that's a very important idea. The prime factorization of an even number always contains 2, maybe a power of 2, but it definitely contains 2 as one of the prime factors. No odd number is divisible by 2. Odd numbers can be expressed in the form 2k plus 1 or 2k minus 1, where k is any integer. The prime factorization of a positive odd number will never contain a factor of 2. All right, well, this is interesting. So 2k plus 1 and 2k minus 1, those algebraic expressions, as long as we know that k is an integer, those are the algebraic expressions for the general form of an odd number. That's important to recognize. It's also important to recognize that if we do the prime factorization of any odd number, we are guaranteed there will be no factor of 2 in that prime factorization. The test loves asking about evens and odds and the basic arithmetic operations, add, subtract, multiply, and divide. So let's get into this. Adding and subtracting evens and odds. Well, first of all, even plus even or even minus even, that's definitely even. If we do odd plus odd or odd minus odd, that's also even. It's only when we mix and match. If we do even plus odd, or if we do even minus odd or odd minus even, the mixing and matching results come out odd. So we can summarize all this by saying if we add or subtract likes, we get even. So as long as we're dealing two of the same thing, two evens or two odds, then we add or subtract and we get an even. It's only when we mix and match, when we add or subtract unlikes, that we get an odd. For multiplying, we also have clear rules. They're a bit different. Even times an even always gives us an even number. Odd times an odd always gives us an odd number. Here, if we mix and match, even times odd, we always get an even number. And if you think about this, the deeper reasoning is the prime factors of the product have to come from the prime factors of the two numbers we multiply together. Well, if we're doing an even times an odd, that even number has a prime factor of 2 as part of its prime factorization. Well, that's going to be included in the product. The product will also have a prime factor of 2, which automatically makes the product an even number. If we think about odd times odd, well, again, there are no factors of 2 in either odd number. And if there are no factors of 2 in the two numbers we multiply together, that factor of 2 is not going to magically appear somehow. It means that we're going to wind up with a product that has no factors of 2. And that's exactly why odd times odd has to be odd. We can summarize and say, as long as there's at least one even factor in a product, the product will be even. The only way a product can be odd is if every single factor is an odd number. That has important implications when we start multiplying more than one number. For example, suppose we multiply 5 integers and get an even number. Then any individual integer could be even or odd. All we know is that at least one of the 5 factors is even. So if someone asks us a specific question, what do we know about C? Well, gosh, anything could be true about C. We're told that it's an integer, but it could be even or odd. We really don't know. we know that somewhere in there is at least one even number hidden. It might be that 1 is even, it might be that 2 are even, it might be all 5 are even. We don't know. There's very little that we know from the fact that the product is even. By contrast, if we multiply 5 integers and get an odd number, well, then we absolutely know, we're guaranteed each one of those 5 integers is an odd number. We know for a fact A is an odd number, B is an odd number, etc. We can draw a clear and unambiguous conclusion about each one of the 5 numbers when the product is odd. Now division. Notice there are no general rules for evens and odds with division, largely because so often integer divided by integer does not even equal another integer at all. Largely, you pick 2 random integers and divide them, you're going to get a fraction or a decimal. You're not going to get a whole number. When the quotient of 2 integers does happen to be another integer, when that does happen, whether that quotient integer is even or odd depends on what factors canceled and what factors remained. It cannot be predicted simply by whether the 2 numbers divided were even or odd. So there are some general patterns, but we can't make predictions. Here are some general patterns. If we divide an even number by an even number, the result could be even or odd or not an integer at all. If we divide an odd by an odd, this could be an odd number or not an integer at all. If we divide an even by an odd, it could be an even number or not an integer at all. And if we divide an odd by an even, that's never going to be an integer because there's always going to be a factor of 2 in the denominator that has no way of canceling with anything in the numerator. And so that's just never going to be an integer. Here's a practice question. I suggest pausing the video and working this question out. So in this question, we are told P, Q, R, and S are integers. If P is even, and P times Q plus R times S is an odd integer, then which of the following must be true? Well, let's think about this for a second. P is even. That automatically makes P times Q an even number. Well, if the sum is odd, the only way we're going to get odd is even plus odd, so that means that R times S has to be odd. When we know both R and S are integers, the only way we're going to multiply 2 integers and get an odd number is if each one is odd. So we know for a fact R is odd and S is odd. We can draw no conclusion about Q because since P is even, it doesn't really matter what Q is. P times Q is going to be an even number automatically simply because P is even. It doesn't matter whether Q is even or odd. We can draw no conclusion about it. So the only ones that must be true are 2 and 3, and the answer is D. Here's another practice question. Pause the video and work on this. If P is an odd integer and P squared plus QR is an even integer, which of the following must be true? Well, first of all, P is an odd integer. Think about this. P squared, that's just P times P, odd times odd. So the square of an odd integer is also odd. So P squared is odd, and the only way that the sum is going to be an even integer if is Q times R is an odd integer. So we have that much. We know that P squared is odd and Q times R must be odd. Now you may be tempted here to say, okay, that must mean Q and R are both odd integers. But let's think about this. We're not guaranteed that Q and R are integers at all. It could be that Q and R are both odd integers, but it could be also that Q is, for example, an even number and R is a fraction. Or it could be that both of them are fractions. For example, with those fractions, 7 over 3 and 33 over 7, if we multiply those, we get the odd number 11. So those are 2 fractions. Their product is an odd integer, but they're not integers at all. So in fact, nothing can be concluded because we are not guaranteed that Q and R are integers. Always be very careful about assuming that numbers are integers. You can't assume that. You have to be very careful with that. In summary, we talked about a few ways of thinking about even and odd numbers. We talked about the rules for adding and subtracting even and odd numbers. We talked about the rules for multiplying. We said that there are no general rules for division, although we did talk about some of the patterns. And then, most important, beware of assuming that numbers are integers when that is not stated explicitly. That is one of the major strategies for any number property problems on the test. Testing cases for even and odd numbers. In the last video, we talked about the properties of even and odd numbers, and we're going to use those properties here. So if you didn't see that video, I'd highly recommend watching that before watching this video. So here we have a practice problem. I'll suggest pause the video here and do this practice problem, and then we'll talk about it. If p and q are integers, and if p squared plus pq is an odd number, what do we know about p and q? The easiest way to approach this is to plug in numbers for different cases. We can simply use 1 for our odd number and 2 for our even number. And notice we're going to have 4 different cases, 4 different possibilities here. They both could be even. Both p and q could be even. Both p and q could be odd numbers. Or it may be that p is even and q is odd, or it may be that p is odd and q is even. So we have to test all 4 of those cases separately. Case 1. P and q are both even, so we're just going to plug in 2. P equals 2 and q equals 2. We're going to get 2 squared plus 2 times 2, 4 plus 4 is 8. That's an even number. That doesn't work. We'll try both odd. Pretend that they're both equal to 1. P equals 1, q equals 1. We plug in, we get 1 plus 1 is 2, which is an even number. That doesn't work. Case 3. P is even and q is odd. So now we're going to plug in p equals 2 and q equals 1. And here we're going to have 4 plus 2 is 6. That doesn't work. That's even. So then the final case, we're wondering now, is it possible for this to be odd? The final case, we'll try p is odd and q is even. Now we're going to plug in p equals 1 and q equals 2. And here we're going to get 1 plus 2 is 3. That definitely is an odd number. That works. And that's the only case among the 4 that works. Therefore, we know in this problem it must be true that p is an odd number and q is an even number. We're able to figure that out from the 4 case method. We might also solve this problem using logic. Think about it this way. Notice if p is even, it automatically makes both terms even. Then we get even plus even, which equals even, and that doesn't work. There's no way we can get an odd number from even plus even. So therefore, p has to be odd. Now if p is odd, the first term is definitely odd. If the sum is odd, the second term must be even. If p is odd, the only way p times q can be even is if q is an even number. Therefore, p is odd and q is even. So that's a way to solve it with logic. Ultimately, solving it with logic is more direct, it's quicker, but it can be a bit harder to learn how to think that way, and the 4 method approach is a little more methodical. That can be good when you're getting kind of warmed up to this sort of problem. Here's another one of these problems. So again, pause the video, and then we'll talk about how to solve this. If p and q are integers, and the quantity 4p plus q is an odd number, what must be true? Let's start with the 4 case method. If they're both even, so we're going to plug in p equals 2 and q equals 2, we get 8 plus 2, which is 10, which is an even number. Now we'll try both odd. We'll plug in 1 and 1. And we get 4 plus 1, that's 5. That definitely works. So case 1 doesn't work, case 2 works. Case 3, p is even and q is odd. So we're going to plug in p equals 2 and q equals 1. And we get 8 plus 1, 9. That's an odd number. That works. So we have 2 cases that work. Now we'll try case 4. P is odd, q is even. We get 4 plus 2 is 6. That doesn't work. So what's exactly is the pattern here? Notice that the cases that work are the cases where q is odd. If q is odd, then the expression is odd. And if q is even, then the expression doesn't work. So the conclusion that we can draw definitely is q is odd, and we really can't draw anything about p. It is definitely true that Q is odd, and we can draw no conclusion about P. Now again, using logic, think about this. 4P must be even, because 4 is an even number. So the only way that the sum will be odd is if Q is an odd number. So Q must be odd. 4P will be even regardless of whether P is even or odd. So whether P is even or odd does not matter at all to the result. If you are still developing your number sense, then you may find it helpful to start with the four-case method of plugging in numbers. Even if you solve the problem that way, it's a good idea to go back and see if you can solve the problem with logic as well. Often a logical solution is shown in the official explanations to a problem. And again, practicing the logical solution ultimately will be a much deeper form of mathematical understanding. Applying the four cases is kind of rote. That's not real deep mathematical thinking. Ultimately, what you want to do is practice your mathematical thinking. In summary, in this video we discuss the four-case method of plugging in numbers to solve even and odd questions, and we discuss logical approaches to such problems as well. Remainders. This is an important topic. So far in discussing division, we have talked mostly about multiples and their factors. When we divide any integer by one of its divisors, that quotient is always an integer, and in fact that integer is always another one of the number's factors. So for example, 21 divided by 3 is 7. Well, 7 of course is a factor of 21. In fact, this is related to the fact that 21 divided by 7 equals 3. Both of them are connected to the fact that the product of 3 and 7 is 21. Those are both factors of 21. What happens when we divide one number by another number that is not one of the factors, one of the divisors of the first number? For example, what happens if we divide 17 by 5? Now, we talked about this a little bit in a previous video we're going to review here. One approach would be to change to fractions. So a perfectly valid answer to that question, what is 17 divided by 5? A perfectly valid answer is the improper fraction, 17 over 5. That number is 17 divided by 5. Sometimes we need to change that to a mixed numeral. Here we can write this as a mixed numeral, 3 2/5. And of course what that mixed numeral means is that there's implicit addition. What that really means is that it's 3 plus 2/5. This is a perfectly mathematically correct answer, and in some contexts this is exactly what's required. Sometimes the test will ask you for some kind of division and the numbers will be listed as mixed numerals or as decimals, and so this is the way you have to go. Sometimes though we want to keep everything in terms of integers. For example, suppose we have 17 identical items and we can form some kind of important set from groups of 5 of these items. So we're grouping identical items. In that case, we'd want to know how many full sets can we create, and we'd want to know how many extra will be left over after we create those full sets. Here, clearly, we can form 3 full sets of 5, and then we would have 2 extra items left over. In other words, the quotient would be 3, and the remainder would be 2. In this video, I will use the term mixed numeral quotient and integer quotient to distinguish between these two types of division. So if we're talking about 17 divided by 5, the mixed numeral quotient is 3 2/5. I could also write that mixed numeral quotient as a decimal if I wanted. The integer quotient, I'm going to state it this way, verbally. 5 goes into 17 3 times with a remainder of 2. That 3 is the integer quotient. So notice that I'm not writing this as an equation, I'm writing that in verbal form. Some of you might have seen in school something along the lines of this, 17 divided by 5 equals 3 remainder 2. That's a slick little notation. I'm not going to use that only because, first of all, some people find that confusing, and second of all, the test never uses that. That you will not see on the test. The test always states this stuff in verbal form, so I'll be stating it in verbal form here. In these problems, find the integer quotient and the remainders. Try and do this without a calculator. Pause the video and then I'll talk about these. 20 divided by 6, well obviously 6 goes into 18 3 times and we have 2 left over. 95 divided by 7. This is a little bit trickier. You have to know that 91 equals 7 times 13. And so it goes in 13 times with 4 left over. 56 divided by 8, of course 8 goes into 56 in even number times. It goes in 7 times and we have no remainder. So for that we can actually just write the equal sign and note that we have no remainder at all. Let's talk about the terminology here. 20 divided by 6 yields 3 with a remainder of 2. What are the terms for all these roles? The 20, the number divided, is called the dividend. The 6, the number by which we're dividing, is called the divisor. Now be very careful here. We're using divisor in a slightly different sense than we've used in previous videos. In previous videos we were talking about divisor as a synonym for factor, the factors of a number, the divisors of a number. So we're not using divisor in its factor sense here, because of course 6 is not a factor of 20. We're just using divisor in the sense of the number by which we're dividing. So this is divisor in a division sense, a slightly different use of the word. Of course 3 is the integer quotient and 2 is the remainder. Well, a few things to notice. First of all, notice that the remainder is always less than the divisor. The remainder has to be a positive number. It could be 0, could be positive, but it has to be less than the divisor. If it were greater than the divisor could go into it one more time. So that's why it's always less than the divisor. If D is the dividend, S is the divisor, Q is the quotient, and R is the remainder, then we can write things in this form. D divided by S, dividend divided by divisor, equals the quotient, the integer quotient, plus the fraction remainder over divisor. So this is an important formula because it allows us to make a connection between the integer quotient and the mixed numeral quotient. Q is the integer quotient, but if we then add that little fraction, remainder over divisor, that gives us the mixed numeral quotient. Now it's very important to realize also Q is an integer, so any non-integer part of the mixed numeral quotient is going to be that fraction. This means that if the quotient is written in mixed numeral or decimal form, the non-integer part of the quotient is remainder over divisor. That's a really subtle and important point. Suppose we're told we divide two numbers and we get that horrible long number with a decimal part. We know that the remainder divided by the divisor will equal that non-integer part, that decimal 0.375, which happens to equal the fraction 3/8. We don't necessarily know that R equals 3 and S equals 8. It could be that we have a remainder of 3 and a divisor of 8. That could be true, but R over S could also equal any fraction equivalent to 3 over 8. So it could be 6 over 16, 9 over 24, 12 over 32, etc. So all we have here is ratio information. We know that the ratio of R over S equals 3 over 8. And if we knew either the remainder or the divisor, we could find the other. One important skill is generating examples of possible dividends that, when divided by a certain divisor, yield a specific remainder. For example, what numbers, when divided by 12, have a remainder of 5? Well, clearly, the simplest one would just be 5 plus 12, which is 17. When we divide 17 by 12, it goes in once with a remainder of 5. Similarly, we could take any multiple of 12 and simply add 5. So all of those are numbers that when we divide by 12, it will go in a certain number of times and then it will have a remainder of 5. And notice we can get from one to the next simply by adding or subtracting 12. So 17 plus 12 is 29, plus 12 is 41, plus 12 is 53. So much in the same way as we can get from one multiple to the next by adding the number, we can also get from one of these numbers to the next by adding the number. If I tell you that 1997 is a number that when you divide by 12 has a remainder of 5, then you could find other numbers of this set by adding or subtracting 12. So we could add 12 and that would be 2009. We could subtract 12, that would be 1985. Incidentally, what we're doing here, we would be finding all the years that in the Chinese calendar were the year of the ox. So I'm mentioning this only because it's a really unexpected application of remainders and divisors. There's all kinds of subtle ways that remainder and divisor questions can show up on the test. Another tricky question is, what is the smallest positive integer that, when divided by 12, has a remainder of 5? Well, you may think that it's 17, but it's actually 5. Well, wait a second. What's going on here? 12 is bigger than 5, so if we divide 5 by 12, it goes into it 0 times, an integer coefficient of 0, and the remainder is 5. In general, if the divisor is larger than the dividend, then the integer quotient is 0 and the remainder equals the dividend. The test absolutely loves to test questions about this. Finally, a very important topic is rebuilding the dividend. What do I mean by this? Above we have that fraction equation. If we multiply both sides of the equation by s, the divisor, we clear all the fractions and we get the equation dividend equals divisor times quotient plus remainder. That formula is immensely important. That is called the rebuilding the dividend equation, and that is an immensely important formula for problem solving. Let me give an example. Here's a question. Pause the video, and then I'll talk about a solution to this. When positive integer n is divided by positive integer p, the quotient is 18 with a remainder of 7. When n is divided by p plus 2, the quotient is 15 and the remainder is 1. What is the value of n? So we're being asked to find the dividend. So using the rebuilding the dividend formula for the first sentence, we get n equals 18 times p plus 7. Using the formula for the second sentence, we get n equals 15 times p plus 2 plus 1, the remainder. And of course I can simplify this to 15p plus 31. Those are two expressions for n, so I can set them equal to each other. Subtract 15p, subtract 7, we get 3p equals 24, p equals 8, and then we can plug in and we can solve for the dividend, which is 151. So using that formula is a very powerful problem-solving tool. In summary, dividing by a number that is not a factor of the dividend, we could get either a mixed numeral quotient or an integer quotient and a remainder. The remainder is always greater than or equal to 0 and less than the divisor. R over S is the non-integer part of a mixed numeral or a decimal quotient. That's the remainder divided by the divisor. We can always set it equal to that non-integer part. One important skill is generating examples of possible dividends for a given divisor and remainder. And finally, we talked about the very important rebuilding the dividend formula. Now that we've finished talking about all the important properties of integers, we'll review the strategies on this very important question type. The first and most important strategy when dealing with integers is make sure you're dealing with integers. Now this sounds a bit paradoxical, but you see the test loves to give problems with variables and set traps for students who automatically assume that the variables represent integers. So yes, you know a lot about integer properties, but don't go automatically applying all these properties if you're not guaranteed that the variables or the numbers in the problem are in fact integers. If the question identifies the variables as integer, they say explicitly x and y are integers, or if they use the words even, odd, prime, then yes, then we do know that the variables are integers, but there has to be some kind of explicit statement. The second most important strategy when dealing with integers is don't forget about zeros and negatives. People, sometimes they just get positive happy. They hear the word number and they think, oh, number has to be 1, 2, 3, 4, 5, numbers like that. They forget about negatives, they forget about zero, fraction, decimals, etc. You always have to think about all possible categories of numbers. So even if you're told it's an integer, it could be 0, it could be negative. Even an odd numbers can certainly be negative, and 0 is an even number. Prime numbers do have to be positive, so if you're told the number is prime, you do know it is a positive integer. Also, the question only talks about remainders if all the numbers involved are positive integers. So that's another case where you know you're dealing with positive integers. Remember the many interchangeable ways to talk about factors. 13 is a factor of 78, 13 is a divisor of 78, 78 is divisible by 13, 78 is a multiple of 13, 13 is part of the prime factorization of 78. All of those represent the same fundamental mathematical fact, and the test uses these ideas interchangeably and expects you to use them interchangeably as well. For the prime numbers, I recommend memorizing all the primes below 60. So those are the prime numbers below 60. Again, it will save you a ton of time if you don't have to figure out, wait, is 59 a prime number or not? It's better just to know that. Of course, remember that 1 is not a prime number. It is conspicuously absent from this list. 1 is not a prime number. And remember that all prime numbers are odd except for 2. 2 is the lowest prime number and the only even prime number. The test loves to ask about that. Remember that prime factorizations unlock all kinds of secrets about numbers. Prime factorization is the single most important strategy for unlocking a number of problems dealing with integer properties. If a number larger than 100 appears in any question, chances are very good that finding the prime factorization of the number will help you answer the question. So, especially if it's a question asking something about factors or multiples or division or something like that, and there's a big number in the question somewhere, chances are pretty good that if you do the prime factorization, it will give you some kind of insight. It's essential to memorize the perfect squares of the first 10 integers, and it's helpful to memorize the perfect squares of 11 through 15 as well. If you know that, you'll save yourself a lot of time. Remember that, of course, you can square 0. 0 squared is 0. And remember that a negative squared is positive. So just as positive 9 squared is 81, negative 9 squared is also positive 81. For questions on which you need to find the greatest common factor or least common multiple, remember the procedures we have discussed as well as that magic formula. And of course, with that formula, remember the danger associated with it. You'd never want to perform the multiplication in the numerator first and then divide. That would be the absolute worst way, the most unintelligent way to use this formula. You always want to cancel because, of course, the greatest common factor, because it's a common factor, it will cancel both with P and with Q. You actually have a choice about how you cancel, but definitely cancel before you multiply. Also remember to practice so that you build your intuition. If you're given small numbers, it's much more efficient simply to use your intuition than apply a formal procedure. It's really one of the traps of studying to try and get procedure happy and trying to memorize a recipe or a procedure for everything. That is not the path to success on the test. You really have to develop your number sense and your mathematical intuition. For questions about even and odd, remember that you can always use the substitution 1 equals odd and 2 equals even. If 2 variables are given, remember you have to test all 4 cases, both even, both odd, and then even and odd either way. And again, this is another case where you can use the procedure, but it's also good to use logic and intuition. That deepens your mathematical thinking. For consecutive numbers, remember that questions about these often appear in variable forms, and you have to recognize that the algebraic expressions represent consecutive numbers. So for example, if we have an expression like this, we factor out the t, we rearrange the factors, and sure enough, t minus 2, t minus 1 times t, that is the product of 3 consecutive numbers. But we know, very important, this is 3 consecutive integers only if we know that t is an integer. We have to have that guarantee. If t is not an integer, all bets are off, and this expression doesn't have any particular meaning. Finally, for all questions involving a remainder, remember 2 powerful strategies are listing possible dividends. For example, listing all the dividends that when divided by 6 could have a remainder of 3, something like that. And the other one is using the rebuilding the dividend formula, which is given here in verbal form. So I'll say math is not a spectator sport. You learn math only by doing math, by solving problems. So if your only exposure to integer properties so far has been what has happened in these videos, yes, there's a lot of information in these videos, but you really don't own it until you solve problems.